What is up, chemistry fans? It's your boy, Cadet Sergeant Ryan Kreiser, back at it again with another banger PChem video. This is a new recording software that I'm using. If you notice a change in quality, it's because the free trial on the other one ran out, and I am very cheap. Before I get any further into this video, please remember to smash like and subscribe and ring that notification bell. If I get to 10 subscribers, I will release YouTuber merch. That's right, you could get my face on a shirt and wear it. Alright, ladies and gentlemen, boys and girls, get ready. Pull your knickerbockers up all the way to your knees, because today we're going to be entering the crucible of chemical combat and defeating Chemistry ISIS. That's right, chemistry fans. ISIS is doing chemistry research and we need to stop them. Alright? Although we've had a technological lead on our adversaries for decades now, it's beginning to shorten. We have advanced intelligence that our enemies have obtained knowledge of kinetic molecular theory. And you may be asking yourself, what is kinetic molecular theory and why should I care? Well, I'm here to answer that right now, gentlemen, and also ladies, and also children. That's right. You may not even remember what kinetic molecular theory is, but Cadet Sergeant Kreiser is here to fill you in. Kinetic molecular theory is based on 3 tenets. Tenet 1, ceaseless random motion of particles. Tenet 2, negligible size of particles. And Tenet 3, brief elastic collisions. These 3 principles define how we view gases in the ideal limit. And we believe that ISIS is using them to understand their own gases, potentially to nefarious ends. Thankfully, our intrepid assets in the field have uncovered a series of data points that chemical ISIS is using to their own nefarious ends, which we can perform big data analysis on in order to determine what exactly it is they're doing. Let's look at this data. This is the X, Y, and Z velocities of 4,000 particles recorded over femtoseconds, showing that our enemies have significant instrumental capabilities. There are about 3 million data points in this data set, which makes it very difficult to analyze with the naked eye. To analyze this data, I'm going to use the program RStudio. You can use a number of other programs, which would be just as effective, but RStudio is something that all cadets learn in their statistics class, and is very effective for handling these large sets of data because of its system of data tables. When you load data into RStudio, which I've done here using the read.table command, it gives the data in the form of a data table, which automatically saves different variables, and then saves the strings as numbers or characters or whatever the correct type of data is, and is able to perform operations on that data. Even with millions of data points, it's very easy to see what the distribution of the data looks like. Here we see the mean and standard deviation of the velocity in the x direction. Similarly, the velocity in the y direction and the velocity in the z direction. In fact, here we can see that the velocity in the x direction is also the median velocity in the x direction. Additionally, RStudio can be used to visualize different data. For instance, here, I've created a histogram to visualize the velocity in the x direction, the velocity in the y direction, and the velocity in the z direction, displayed in red, white, and blue because this is America. As you can see, the distribution for all these velocities is approximately normal, which hints to the idea that we could have a Boltzmann distribution of speeds. Here, you see the power of R as I create a new data table using the square root of the magnitude of all the vectors here, the x, y, and z direction squared. This creates the magnitude of the total velocity vector for each molecule at each point in time measured in this data set. As you can see, this data creates a histogram that approximates the Boltzmann distribution. The Boltzmann distribution starts at 0, appears approximately normal, but is skewed right as time goes on because particles can't move at less than 0 velocity, but they can move pretty much as high as you need them to.
Yeah. I landed 3 body shots.
Here I display 3 different center points that you can refer to this distribution with. Here's the region of highest probability, which is essentially the median of the data. Over here at 0.00388 angstroms per femtosecond.
Oh, we can just hurt the primary.
Here is the root mean squared. This red line over here, which is the mean of the distribution when you square all the values and then take the square root of that value. And here is the simple arithmetic mean, this green line here. This is exactly what would happen if you took all these magnitudes and took the average. Another advantage of R is that it allows you to pretty easily load more data in as time goes on. Here you'll notice I've read the total energy data that our intelligence assets have provided, the kinetic energy data,
Dominic the asshole was.
and I can do the same thing with these sets of data. Here I have a histogram showing the kinetic energy is also approximately normal, with the mean here and the standard deviation in one direction or the other. In the same way, I'm able to do the same distribution with total energy, with the mean and standard deviation, just as I've done before. I also load the pressure data and perform the same operation there, with the mean and the standard deviation.
I see him. Oh, I can't fucking.
Finally, in order to make sure that these normal approximations aren't just an artifact of an actual trend going on in the data, I plot the scatter plots of all these data points.
I don't know.
As you can see here, the total energy appears basically random. The kinetic energy appears basically random. And the pressure appears approximately random over time.
Yeah, that's what I'm saying.
This is important because if a trend showed in our data, it wouldn't matter how normal it appeared to be, it would still be inadmissible for the Boltzmann distribution. Using the equation kinetic energy equals 1/2 mv squared,
What?
and by using the mean kinetic energy and the mean velocity from the mean velocity vector that I calculated earlier, I was able to determine the molar mass of the molecules. These numbers here are mostly for scaling factors because kinetic energy is a function of velocity in meters per second, and velocity was given in angstroms, which are meters times 10 to the negative 10 per femtosecond, which is seconds times 10 to the negative 15. I got the molar mass of the molecule in question is 27.27 grams per mole. While there are other ways to calculate this quantity, such as the density that was given in the initial data set, mass measurements and density measurements are pretty inaccurate at such small quantities. Therefore, I thought it was best to extrapolate from the kinetic molecular data what the mass must be for the kinetic molecular data to be true. The last thing I needed to do was calculate the temperature of the system. I accomplished this by using the ideal gas formulation of the equipartition theorem, which is the idea that 1/2 mv squared contributions from the x, y, and z directions equals 3/2 RT for a spherical molecule with no vibrational energy. By assuming ideal behavior, which is already implicit in the kinetic molecular theory, I was able to determine the temperature of the system in Kelvin was 2/3 the mean kinetic energy divided by R, the ideal gas constant. I now understand the temperature of the system must be 210 degrees Kelvin, which is about negative 60 degrees Celsius. Well, there you have it, ladies and gentlemen. By using the kinetic molecular data obtained from our intelligence report on chemical ISIS, we've determined the molar mass of the molecule they're studying, what the temperature of the system was, and that their instruments are able to accurately depict the Boltzmann distribution and prove kinetic molecular theory at the ideal limit. But what could they be doing with this information? Based on the kinetic molecular data, I believe that chemical ISIS is currently studying hydrogen cyanide, which has a molar mass of 27.05 grams per mole, as opposed to the studied molecular mass of 27.27 grams per mole.
Okay.
Why this higher molar mass?
Came in clutch.
I believe that chemical
just
ISIS
tested all their
could be attempting to enrich hydrogen into deuterium by using kinetic molecular sieving on hydrogen cyanide gas in order to collect as much deuterium as possible. What could they be doing with deuterium, you may ask?
Pull this out.
Well, deuterium is used in nuclear reactors, but in World War II, Nazi Germany attempted to use deuterium to make an atomic bomb. Well, that about does it for today. Thanks for sticking around till the end.
Yes.
While this was a departure from the normal tone of my videos,
No.
I thought it
Just
would be a fun departure and one that wouldn't detract too much from the science and the data at hand. I hope that this video has been of some use to you and that you have a very thermodynamic rest of your day. Spaghetti with beef and sauce. Take care now.